So, welcome everyone to today's talk of Professor Lingjie Liu, who comes from University of Pennsylvania. Currently, she's assistant professor there, and she's affiliated to the Department of Computer and Information Science at the university, where she leads the Penn Computer Graphics Lab, and she's also a member of the General Robotics Automation Sensing Perception Lab. And previously, she was Lisa Meitner postdoctoral researcher fellow at the Max Planck Institute for Informatics, and she received her PhD degree from the University of Hong Kong in 2019. And her research interests are at the interface of computer graphics, computer vision, and AI, with a focus on neural scene representations, neural rendering, human performance, modeling and capture, and 3D reconstruction. So we are very excited to have Lingjie here today. So the floor is yours. Please take it away.
Yeah, thank you, Xi, for the kind introduction. Hello, everyone. This is Lingjie Liu from UPenn. I just realized that this week is a super busy week for the new IFS deadline and for the ICCV rebuttal deadline. So I really appreciate you attend this talk. If you have any questions, just interrupt me. In today's talk, I will talk about towards the next gen 3D reconstruction and generation. So first, as a motivation, why we care about 3D. So this is my favorite shot from France when Chandler was proposing to Monica that you can see here, like we live in the world that is the 3D, and we have our friends all interact with each other in 3D, and we have the 3D environments. So we live in the world that is the 3D and contains the dynamics. That is why we want to digitize our world in 3D. So we can immerse ourselves in this virtual environment. We can also like interact with the virtual characters or the real people via the AR technologies. And also for the future AI, I think need towards 3D aware, because we want like this AI technologies to help people interact with the people. So we hope like this AI system to also care about this 3D, where the 3D, how to help people, how to interact with the people, how to complete the task with with human together. So for my research, the long-term research vision is that we hope to build the AI technologies for our 3D task to help us to digitize the 3D real world in the virtual world. At the same time, we hope like this 3D technologies could help us to enhance like the AI technologies, so make the AI more 3D aware. So at the beginning, I want to share like my journey in like this area, like 3D reconstruction and the generation. Like starting my PhD, I first learned like this image-based reconstruction methods. I think all of you have learned in your computer vision courses, like this is a given multi-view images, and you can estimate the camera parameters for all these images, and also we constructed the 3D geometry and appearance model of this object. So this is a like amazing technique, because like even recently with like all these deep learning methods are developing, we're still using like the classical method to get the camera poses or like get the initial point cloud. However, if you I think like a camera poses from this traditional method is perfect, and also the cost geometry. However, if you want to get very fine-grained, detailed 3D geometry and models that you can use, for example, for some computer graphics applications in either physics-based rendering techniques or physics simulator. It's still like there is a huge gap between the reconstructed without from traditional image-based reconstruction method and the required quality for the computer graphics applications. And then back to 2014, I think the first paper is the OpenDR, and then they have some follow-up works like deep voxels, neural volumes, SRL, and NERV. And they proposed like a new way to 3D reconstruction problem. So the core idea is that, so previously we have like this pipeline, we have input images, and then we reconstruct the 3D. And then we can also like render out this 3D reconstructed geometry and appearance models and to get the render images. So this method, they like formulate this image synthesis process as a differentiable render. In this way, like you can compare like your input images with your rendered images and calculate the loss and then back propagate the gradient through like a differentiable rendering to your 3D reconstruction. And as a follow-up work, it's what we call news, and then we started like looking into this area, and then we found that like there is the one limitation of NERV is that if you use the matching cube to extract the surface, the surface has a like noise because this is not the surface representation. So in this work news, we used like a volume rendering proposed like in NERV and also the previous work. And then we present the 3D geometry at the sign distance field. And in this way, we can learn a good surface representation from multi-view images. So as you can see here on the left, we have the multi-view images. We also have like the camera parameters from the traditional methods, structure from motion. And then we can reconstruct a high quality geometry and appearance models, and then render this from normal views. And then like 2 years later, we want to accelerate the training process of this method news because previously it's took like 10 hours for one scene. So in the news tube, we accelerate this into like just 2 minutes. You can get your 3D reconstruction. We then extend this to the animatable human modeling. So here, like instead of using like multi-view images, we use multi-view videos. And then we check the skeleton for these human motions and then predict different components like the cost geometry and fine-grained geometry and also texture map. And they use the differentiable render to render this into images and say the same way as we did before, like we calculate the loss and make the gradient back propagate to these three components, the geometry and the texture map. And also, since like this is animatable, the human modeling method, what you can do is that you can not only reconstruct the thing, but you can also synthesize the human human under like a novel motions. So you can give like the input, the novel skeleton motions to drive your virtual capture to move as you want. And so this work was has done at the MPI. When we capture the data, we used like this the studio, the green screen the studio to capture this data. I think like at the ETH you also have like this screen green screen studio at the Optimus lab. So here, like for example, for like our methods, like we need to capture this with the synchronized 120 synchronized and calibrated cameras. You know that as the normal person, you may not have like the access to this studio. So we found like multi-view data is very difficult to access. Then we want to think like if instead of using dense view as input, could we use like reduce the number of views? And then this is a problem from which is previously called 3D reconstruction problem, and then now moves to 3D generation problem. Because in this setting, you reduced the number of views, and so which means that you cannot see the back view. You need to generate something which is unseen in your input view, and also like this would raise a lot of uncertainty issues. So for 3D generation problem, it's not only like given the input image, but you can also give the text as input, or there is a no condition. You just add like some noise samples and then to generate the 3D. And the good thing of a 3D generation is that we can generate a lot of data. I think previously for the 3D tasks, the main bottleneck is that we lack of very high quality, large scale data. But if you use you can develop this 3D generation algorithms, you can generate a lot of 3D data. So what is the current status for 3D reconstruction and generation? So here I list, so previously I introduced the pioneering works and also my work. Actually, there's a large amount of work in this area from different groups. So it's a very popular area. And we also have witnessed fast progress in this area, like almost like every 1 or 2 months, you can see like a lot of papers and to improve the quality. However, what is still missing in the existing methods? So another question is that what would be the next generation of 3D reconstruction and generation? So I think in the next generation of 3D reconstruction and generation, first, we need to, because we have seen the great progress in multi-modal generative models, like they use the text, use images, use the videos to train very large multi-modal models. If we can use, for example, all these these models to benefit our 3D tasks, to help us to improve the quality, to help us to resolve the uncertainty issue that I just introduced. And also another problem is that I think most of the current method focused mainly on the geometry and appearance. I think this is also like a long history, like people care about like these 2 properties, geometry and appearance. However, because currently, I think also the development of the robotics, and also we want like our virtual world to not only just to reconstruct the real things, we want to synthesize the new things, which means that we not only care about the geometry and appearance, but we also care about the physical properties. And we want that after we getting the physical properties, that we can ground like our 3D reconstruction in the physical world or in the virtual environment. So in this talk, I will first focus on this 2 parts. I will first introduce how could we leverage multimodal generative models to help us to do 3D reconstruction and generation. Okay, so these are some list of multimodal models that I think we now use this every day, like ChatGPT or video models or text to image synthesis models. So go back to our previous problem, for the 3D generation, especially for single image to 3D generation, the main problem is that we don't know the back view. So we need to hallucinate what is the new content in the back view, and we want to synthesize that. And so there is like a serial uncertainty problem, how to solve this. So could we use, for example, the existing, the multi-modal or the 2D generative models specifically, to use these 2D models to help us to generate the novel views given this single image. And then after we have like the novel views, we can like use the traditional multi-view reconstruction method to get the 3D geometry and appearance models. However, we found that if you directly use, for example, the 2D generative models, you get this issue. This is the we call it the multi-phased problem, that you can see like this elephant, it have multiple heads. And what's this problem? It's because these vanilla 2D diffusion models are not 3D aware. So they don't know this is the front view or this is the back view. How many heads do you need, and how many heads that is synthesized by the model? So could we make like this 2D diffusion models 3D aware to solve this multi-phase problem? And in this work called Wonder 3D, so we proposed like a multi-view diffusion to solve this problem. So the key idea is that previously, if you use the vanilla 2D diffusion model, you sample different view independently, and then there is no multi-view consistency. Instead of doing this, could we jointly sample multi-views together? So we jointly sample that and to enforce multi-view consistency. And also here, things like we generate multi-views, so we can use the pre-trained 2D diffusion models. So here we use the stable diffusion model, and give the input image, we not only just input the novel view, one single novel view, but we output like the multi-views. And also not only the RGB images, but also normals, because the normals contains the geometry information. After you have this multi-view synthesized images, you can fuse them into to 3D. So you have like a 3D geometry and appearance. And here shows the result. So just given a single input image, you generate the normal max and the RGB images from different viewpoints jointly. And then you use this generated novel view images and to get your 3D model. And not only for like using the single view image as input, we just talk about we can use the text as input. So here is another work collaborated with the people from UCSD. You can give a text and you generate an image first, and you lift this into a 3D for the scene level generation. And also, not only for the static things or the static object, you can also do this for human motion generation. For example, as shown here, like in our work, TL control, you give the text and the trajectory as input, and you generate the human motions. Okay, so what is still the problem in either like this, especially this text to 3D model? And we found that there is the missing alignment between the text and the 3D. So for example, if you want to synthesize the text like a teddy bear pushing a shopping cart with his right hand and holding this blue with his right hand, sorry, and holding the balloons with his left hand. And you can see like this generated result don't reflect the input text. And also like on the right, the example like a blue clock and a right cup. And this cup is not right, white is the blue. So like when we generate some things, like we found that this algorithm cannot reflect your input text. And this also happens in the human motion generation. So if you want to generate, like for this text, like a man kicks with his left leg and then kicks with his right leg, and you can see you either have like some problems of like missing this right kick, or it's the incorrect kicking order. Maybe you first kick with the right leg and then left leg. So which means that you generate these 3D things, it's not well aligned with your input text. So how could we solve this problem? So when we used like this the large models like multi-modal generative models, we need to be care about we care about like could we make like this alignment between not only image to 3D but also text to 3D. All these modalities can be aligned quite well. So in this combo, we proposed a way that in this latent space of the human motions, it's a need to have the corresponding semantic meaning. So this is a core idea. If we review like what's have been done in the previous work, we in this task, we first need to train the autoencoder, which means that given like this motion sequence of a human, you first encode it into some latent space, and then you decode it into motions that like to reconstruct these motions using reconstruction laws. However, this latent space always have like these numbers, but you don't know what's the meaning of these numbers. So if, for example, during your generation process, if you get like these numbers, you don't know what is the problem. And then how could we make this latent space more semantic meaningful, or what kind of the representation should be used in this latent space for human motions? So we found a very interesting work. This is a work called PostScript. They used like natural language to describe your pose, which means that for example, like the angle of this joint, or like the distance between your two legs and like other properties. So decomposing like these emotions into this semantic pose codes actually can encourage us to generate more fine-grained and interpretable details. So in this work, Como, we also, like as the previous work, we also used the encoder and decoder to learn this latent space for the human motions. However, we have, for each latent code, we have the code book. For each code, it corresponds to the specific meaning. And in this way, like you can understand what is learned in this latent space. And also, okay. Okay. And then since like you have this latent space, and this latent space is semantic meaningful, we could also use the like GPT to help us to enhance the input text. For example, input text could be very coarse, like the person is kicking, but you don't know a lot of details how to achieve this emotion. So you can use the GPT to generate a lot of like fine-grained steps, and then to encode this to predict your latent space code. Seems the problem. There is the problem. Okay, cool. And then if you, after getting this semantic meaningful latent space, and you can see here, like you can solve this the problem we showed before. Yeah, sorry. Okay. as you can see, like this person actually is the first kicks with his left leg and then with his right leg. And another advantage of this method is that you can do this motion editing very easily because you can do this in the latent space. For example, you first synthesize some motion, and you have this the latent code, and you have the added instruction you want to, for example, to slightly change this motion a bit. And then you can use you just plug large language models and ask them to modify this latent code directly. And so this is a demo, like we show, for example, when we generate some motions, so you can see like which latent code had been activated. So it's very easily to help you to like debug if you found like the final output is not reflect your input text. And also if you want to do some editing, you can just edit that, and then you, it would activate some the latent code. And so you can see here, like first, like you generate some motion. So this is the first generated motions by Como. And if you want to edit that, you just want to have, for example, this the minor changes, like make the bump more dramatic. And you can see like this added motions, it's still like preserve the key the components key motions that like in this source motion, but it's also reflected these added instructions quite well. But for other methods, you get some problems of like do the motion editing. And in this project, we found the very serial issue is that so this is a kinematics-based motion generation, which means that it's like you just learn the motion priors from data, from like mocap data. And it would produce some artifacts, like this physically implausible artifact, like the foot sliding, the floating, and also very unrealistic hand and floor interactions. This is not happen like in the generation task, but also for the reconstruction task. If you see here, like you have the video as input. If you see like this checked motions, it's very unrealistic and unnatural. If you, as a human, you can immediately see, oh, this is not like the post human can make. And also, like in the human object interaction, you can see like the object is also the reconstructed object is also very unnatural, and the interaction between the human and the object is very unrealistic. So then we need to solve another problem, is that how besides geometry and appearance, how could we get some physical properties and to in this way, like we can make like these humans that can interact with the 3D environment and to synthesize the more like a very diverse and realistic the motions. And in this work called model scale, this is our first attempt to do this problem. And we want to address the physical implausible issue. And we found that like this kinematics method, actually they only capture the distribution of motion data, but disregard underlying physical laws. And how could we make this synthesize the human motion to be physically plausible and aware of some physical laws? So here we get inspiration from the robotics community. Like you need to put like your the avatar in either like a virtual environment or real environment. So here we put this in the virtual environment, which is a physics simulator. So we want to learn like the skills or like this policy model, which embedded some skills of the human complete like tasks. And then you put like this physical captures in this virtual environment and to interact with the 3D things. And so one problem here is that when we like train this policy, this we call it imitation learning because this policy want to like mimic what is the motions in the database. For example, here we use a master dataset. A master dataset contains very diverse and dynamic motions. However, for this policy learning process, actually it's very greedy. It can normally it's hard to cover the like distribution of like this large distribution. So how could we solve this problem? And we get some insight from also like previous the human motion generation task is that for like our humans, when we do some tasks, we don't like do this for the full body. We often do this for like certain body part. For example, the left arm, the right arm, left leg, right leg, or the torso. So which means that could we learn like the body part level, the motor skills, instead of the full body skills? Because in this way, for each body part, the skill space can be very compact. So it's easy to learn, and also it's a better representation because it's compact. And here we need to mention that is that this body part, when you divide this into certain body part, you need to be there is not any decomposition. It's the valid. Because here we want to learn the skills. What is the skills? It's that like it's the way like how could you like achieve certain tasks. So if you have primitive skills, you can compose these skills and to complete some tasks. So here if you, for example, you divide it into very small pieces, like just one finger. For this finger, it's hard to like finish a lot of tasks. So that is why you need to have like a quite reasonable decomposition. And in this work, we tested like two decompositions. First is that like as shown here, we have 5 parts, like left arm, right arm, because we often learn the skills is for like this arm part. And or the upper body or lower body. So like this part actually can be divided, like these skills can be divided. Also, like it can achieve some tasks. And also another advantage of this, the modularization of like a different body part skill learning is that this would make this skill learning more flexible. For example, if you only have the full body data set, you can train like this for full body. You have like some hand data sets, like you can train this for the hands. So after that, you can combine them. It's like a very flexible. If you like have like full body data set, which means that you require this data set have the full body as well as hands and have limited data for training. So this is like our design. This is like this physical agents. And also like we have the reference motions from a master dataset. At the beginning, we don't want like each part to be very orthogonal. So here we use the attention map to share some information from different parts. And after that, we will predict the skill embedding for different parts, like left leg or right leg or the armed part and the torso. And then we compose these skills together, and then make like this the physical character to deploy this in the physical simulator, and then to predict their next step. Okay, and then we found the problem is that for as I mentioned before, like even that you have this modularization part, like this imitation learning is still quite greedy in some sense that it's often want to learn some simple skills, not very complex skills. So if you like get a lot of the motion data for them to train, they often like overfeed this to some simple skills that they refuse to learn some the complex skills. So here we used we proposed the active learning. This active learning is that when we detect that there is some imitation task which skills which is failed to imitate, and then we will use our previous text to motion models to generate more samples. And also here we will train a discriminator like to filter out some very obviously artifacts or the unrealistic motions. And then we used this sampled this motion data to help to populate our motion data set and to enforce this policy to learn some complex motions. Okay, and with the this designs, and as you can see, so this is, for example, you generated the motions, for example, from Como. You can generate this motion. This motion is not physically plausible, and then you can make like this physical capture to follow this generated motions. So this red point are the joint of these generated motions. And if without the skill modularization, it cannot fit or check this very well. However, if it's a realistic, if it's with the skill modularization, it will become more realistic. And also, this is another the challenging motions. And you can see like with the skill modularization, you can fit this fit like generated motions very well. And also a very important thing is that this skill is the learned skills are reusable, which means that it can not only to check the certain motions, but it can achieve some tasks. This is what we want when we generate some, for example, physically plausible and realistic motions in the virtual environment. For example, you can give, for example, the direction, like ask this physical character to follow this direction, or if you want to to punch this box, and then you just define like this reward function, and we use this skill to achieve this task. And also, this is also my favorite the application of this method is if you only have the sparsal point. Normally, it's hard to, for example, generate very realistic motions, but with this techniques, you can make like your this physical capture to follow this faster checking point, as well as to generate the other part, which is physics aware. And another thing, as I mentioned before, like you can train like different body parts separately. Like here, like you train like this on the hand data set, and then you can add this to your existing full body policy, and then you can get like this without. So you don't have to train the body controller from scratch. And also you can do this, use this techniques for human and human interactions to generate very interesting motions in the virtual environment with the people interacting with each other. Okay, so here I'm going to talk about like human poses. Actually, if we want like this, the human motions to interacting with the environment, we want like this environment, this 3D environment or 3D object also have the physical property, and not only to reconstruct the geometry and appearance, but it can also have a physical properties, so it can be imported into physical simulator and to do some simulation ready motions. In this work, like with to theme, like motivation is that it can be used, for example, for robotic manipulation or for the digital twins if we want to synthesize some of physical, plausible, the human motion. The human and object interactions. We need like this object also has the physical properties. And so the previously, the existing work employs this heavy parsing optimization, and it often takes hours to reconstruct one thing. This is because this method, first is the parsing optimization. Also, like their representation has a lot of parameters that so makes it quite a long time to overfit into this one thing. And also, like this parsing optimization lacks the generalization ability. So in this project, our design is that given the video input, could we first use the feed-forward models to predict the initial guess of all of these properties, physical properties and appearance and the geometry properties, and after that we can refine this initial prediction and to optimize that. And the key issue here is that we need to find how could we make, for example, from like a parsing optimization to this feed-forward method. It's require that this representation of the object has just a limited number of parameters. If you have a lot of parameters, you can imagine the workload of these feed-forward models and also like these optimization methods. And then in the last year's SIGGRAPH, we found a very interesting paper called Simplicities. So instead of use the previous method, they often use the NPM. For NPM, you have a lot of the voxel grids, and then you need to learn a lot of parameters here. And in this Simplicities, they proposed that use this LBS representation. So you have like the very sparse set of control points, and then you learn like this scaling weight between this control point to represent the movement of any 3D point. So actually, this is quite similar to me because it's often used in for the human modeling. We often use the LBS to model in this way. And this, like in the simulation, this is also quite useful, especially for the inverse simulation problem. And also another advantage of this representation, so here I would not go into details, but if you use the LBS representation, you can use the implicit Euler solver, but previously if you use the NPM, you only can use the like semi-implicit solver. So there is the like computation time difference between these two solvers. Okay, so for our methods, as I mentioned, like for the first stage, you have the multi-view videos. You use the single view video, and then you use the video like a pre-trained video model, and then you fine-tune this to predict some physical property, like Young's modules and Poisson's ratios or LBS weights. And also, like you can reconstruct the 3D Gaussian splats. This is or like another representation, which is similar to. Sorry. So this is like a very popular representation. Like previously we have a nerve, and then currently we have like a 3D Gaussian splats, like more explicit representation. And then for the second stage, like you can refine this this optimization. Like if you have the initial guess, actually this makes the this object is the simulation ready, which means that you can import this into simulation and to do some like a simulation task. And here, like for the optimization, for the refinement, you can also like do the simulation and calculate the loss and also refine like both the geometry, appearance, and the physical properties. And here we show, we will skip some details due to the limited time. And here we show some without. And you can see like our method, like it's much faster than the previous work because it's kind of the combination of a feed-forward process and very lightweight fine-tuning process of a refining process. And also like, okay. And if you see the results, so we compare with the reference and with other results. So our prediction is not perfect because you can see there is also some uncertainty in this the simulation process. And however, it's a very looks very reasonable and also close to the reference videos. And we also tested in the real world case, and it's can perform quite well. And the things that you have for the physical property, so you can change your physical properties, like for different materials, and to synthesize the like motions with the for different materials, and you can add like the boundary conditions as you did in the classical physics simulation, and to synthesize the very interesting videos. Okay, so what's next? I think currently we mainly talk about how to reconstruct and generate static things or humans. But actually in the virtual environment, what we need is more about like a human object interaction. As you see here, like we have these physical characters in this virtual environment to interact with the 3D environments. And in the real world, we also have like a lot of these things, which it's a very complex, like these human thing interactions. And there are a lot of constraints, like physics constraints, environment constraints. How could we reconstruct these things in this virtual environment? It's still a very interesting direction to explore. Another thing is that we talk about how could like the multi-modal generative models that help the 3D reconstruction and the generation, and also how to make our 3D reconstruction and the generation to be physics grounded, so it can can be ready for like the real world applications, or can be in the virtual simulators that like we can. Like physics simulators, that it can be simulation ready. But another, I think, very interesting direction is that currently in these multimodal generative models, that we often we didn't use the like 3D data. This is one thing is because we have limited 3D data. And how could we make like this 3D reconstruction and the generation techniques that also benefits the multimodal generative models learning? Because as we can see here, like this is the video from Soro. I think like people are quite familiar with that. When you just learn this from data, from like videos, sometimes it's lacks of some constraints. It's like you can not see, this is a very unreasonable, like this trail is floating and everywhere without like a very reasonable interaction with the people. And how could, so here, how could we introduce some 3D inductive bias, or we can use some generated 3D things to help to also benefit the multimodal generative models. This is, I think, also a good direction to explore, and also a fundamental issue in the multimodal generative models. Finally, I want to thank all my co-authors. Without them, I cannot present this work to you. And that's all. Thank you, everyone. Any questions?
Thanks, Lingjie. Thanks a lot for the talk. Yeah, if anyone has questions, please just unmute yourself and feel free to just speak. I can get started. So I find this COMO framework really cool, but was really wondering, how do you really enforce the structure in the Learn code book? Like, how do you enforce that? You know, the first one is about the right arm, and then the second one is about the left arm. What is the trick? What's the magic there?
I think here we first we have the reconstruction loss, which means that after you code it into this code, after the decoder, you can reconstruct like the same motions as your input motions. So this is a one loss. Another thing is that we also use the postscripts to give us the like some the supervision in the on this latent code as well. So we have like two parts of loss, like this reconstruction loss, to ensure us this decoded motions from this latent code is reasonable. It's like the real motions, and also this the latent code loss would like enforce this to map it to certain semantic meanings.
Yes, get it. That's really cool. Yeah. If anyone has any question, just feel free, right? I can ask another one, which is related to this two-stage training for generating physically plausible video sequences. So I assume the training data doesn't have all of those ground truth physics properties, right? Like what you have at the stage one, and then it's passed to stage two. So is it just really just like learned through end-to-end training? Or is there some supervision signal in between?
Yeah, let me go back to that slide. Here we first used actually we mainly used the synthetic data for training. So which means that we will like synthesize a lot of data in the physics system later. We have like this ground truth, like this physical properties, and we train this like in this way, like in a supervised way. Yeah, so but we found that it can generalize to real data quite well.
That's cool. Yeah, we have a question from Deng Xiang. Do you want to speak up by yourself, or should I read it? So, okay, I can read it. So what he wrote is, yeah, thanks for the great talk. When your generative model simulate object spinniness and dynamics, does it also take into account the physical properties of the background? For example, surface friction, obstacles, gravity fields when predicting motion?
This is a very good question. So currently we didn't handle this. This is also very difficult to predict from RGB images. For example, like this fiction, the surface fiction, because if you see like from the videos, it's a little bit hard to predict this fiction. Yeah, so we ignored the background at all. We just synthesized currently. This is the kind of the first step. We just synthesize the object's physical properties. And this is a good question. I think in the next step, we want to, for example, to extend it to more about to considering like the background and also the interaction of the object with the background.
Cool. Yeah, thanks also for the yeah. Maybe one more last question from my side. What do you think is missing for like integrating or injecting this physical knowledge into the 3D generation pipeline as you talked about next, right? Like, do you think like it could be solved with more 3D data, or there are some other ways? And what do you think is the bottleneck for this, for tackling this problem?
Oh, this is a very good question. We are also thinking about this problem for quite a long time. I think the currently the main issue here is that how could we present this physics? Because I think the thing is that we for the physics simulator sometimes it's a little bit hard to use. It's very sensitive to the parameters and a lot of parameters for the physical simulators. And how could we present this physics? I think this is kind of the key issue. I think another problem is that how could we how to inject this physics priors into multimodal models is another question, because for example, currently, I think not if we not talk about the physics, we just talk about the 3D. In this multimodal generative models, normally people don't use 3D. I think there is two reasons. One is that we lack of 3D data. Another thing is that it's like a 3D representation. It's very costly compared to you encoding like this 2D image. So currently, people use for example, instead of use 3D representation, they use the multi-view images of this 3D and then feed this into the multimodal training process. So I think like for 3D, we have like this problem. For physics, we also have like this issue. What kind of good representation of the physics would be easily to be integrated into the large model training? I think these are in my view, these are two very fundamental problems. Like how could we give like this generative models the more 3D or more physics priors?
Okay, get it. Thank you, Lingjie. Cool. Last chance.
We should be able to find this out.
All right. All right, cool. Seems like it was a clear talk. Everybody gets it. So that's really cool. So thanks a lot, Lingjie, for joining us. And thanks everyone for joining. Then hope you still have a nice day or a nice evening.
Yeah, thank you. Thank you. Thank you, everyone.
Bye-bye.
Bye.
Bye-bye, everyone.